In this lesson, we're going to look at another special type of triangle called a 30, 60, 90 triangle. And that term 30, 60, 90 comes from the idea that if we take an equilateral triangle, and so we're going to make the assumption that all three sides of this large triangle are the same length. So if this side length was 2, this side length would be 2, and all the way across here from one side to the other would also be 2. So equilateral means equal length. So all three sides the same length, which means all of the major angles, this angle, and this angle, all three of those would have to be the same length, which in a triangle they add up to 180 degrees. So each of these would have to be 60 degrees all the way across. And this one would also be 60 degrees all the way across. But if we cut it in half with that line down the middle, each of these would be 30 degrees. And then here at the bottom where we bring this line down, the center of this triangle creates two 90-degree or right angles at the bottom here. So what we actually create is a 30, 60, 90, two of them, 30, 60, 90-degree triangles. Now what that does is that when we take an equilateral triangle, cut it in half, we also cut the bottom in half. So this 2 becomes 1 and 1. So we have a distance of 1 here, a distance of 1 here to make up that 2 all the way across. The other piece we want is this length of this line that cuts it into two pieces, the equilateral triangle into two separate pieces. And you can find that by just working the Pythagorean theorem backwards. We have a hypotenuse side of 2, so we would square that, which is 4. We have a leg length of 1, and so we would square that. 1 squared is 1. And so to get back to this piece, we have to actually subtract 4 minus 1, because this is a hypotenuse and a leg, and it's the legs added together. So this squared plus this squared make that. So this would have to be a 3 for an area, or the square root of 3 for the length. So and again, I'm just using the Pythagorean theorem sort of backwards, thinking of the idea of we have a leg squared, we could call it a squared, we don't have it, plus the 1 squared equals 2 squared, or whatever this a squared is, plus 1 equals 4. So you see that a squared, this a squared piece would have to be 3, so a is the square root of 3. To take the square root of that area to get the side length. So now I have all of these parts. The length of this, each of these becomes 1, and the original piece is 2. Now there's a pattern that arises with 30, 60, 90 triangles. So if I take another one and I just say that this length, the side length is 4, which means this one would be 4, and all the way across here would be 4. And again, there's a 60-degree angle there. We have the 30-degree angles up here where we cut 60 in half. That one remains 60, and then our right angles down here where this line comes straight down. Now by cutting the bottom in half, then each of these pieces is 2. And then when I go to find the length of the leg, this other leg, we have a hypotenuse and we have a leg. And again, I use the Pythagorean theorem backwards. So I'd say 4 squared is 16 for the area of the square out here, the c squared, if you think of it that way. So we square this is c. And then the other leg, the 2 squared. So now I have the hypotenuse and a leg, so I got to work back to the other leg. So this plus 4 equals 16, so now I know that has to be a 12 for the a squared is 12, so a would be the square root of 12 for that length. Now the interesting thing with this is if I take the square root of 12 and I simplify it, so we can simplify radical expressions sometimes, when they have factors that are square roots. And the square root of 12 can actually be factored to the square root of 4 times the square root of 3, which means that the square root of 12 is the same as 2 square roots of 3, because the square root of 4 is equal to 2, and this one we just leave alone because we can't really change it, square root of 3. It's not factorable, it's not solvable in a whole number form, so we'll leave that alone. So this distance here is actually 2 square roots of 3. Square root of 12 is equal to 2 square roots of 3. So you might be able to notice that there's a pattern that develops. We do this again and again. I'm just going to use different lengths to see where the pattern rises. So if I call this length 6, that means this side is 6, and that means that all the way across here is 6, which means from here to here is 3. So each of these is 3, make up the 6. I still have my right angles, 60 degrees in the corner, 30 degrees at the top. So I have 2 identical 30, 60, 90 triangles. I know this length and this length. I want to find this length here. And so again, if I use the Pythagorean theorem backwards to work back to that other leg length, 6 squared would be 36. 3 squared would be 9. And 36 minus 9 would be 27. And so this length would have to be, that would be a squared. So I need to take the square root of it to find that length. So the height of this is the square root of 27. And again, that might not seem like it's very helpful, except if I were to simplify the square root of 27, can actually be factored to the square root of 9 times the square root of 3. And the square root of 9, I know, is 3, and then the square root of 3. So really the square root of 27 is the same as saying 3 square roots of 3. Now, I hope by now you might notice that in all of the lengths that cut the equilateral triangle in half, that the one thing they have in common is the square root of 3 in each of the lengths when we simplify the radicals. You don't really notice it with the square root of 3 and the square root of 12 and the square root of 27, but if you simplify them, you can see that this one is 2 square roots of 3, this one is 3 square roots of 3. I'm going to make one more triangle, and I think maybe you might notice if I say this is 8, and this is 8, and all the way across here is 8, equilateral triangle, and again I have my 60, 30, 90 triangles all the way around. So halfway across is going to be 4, and this length right here is then going to be 4 square roots of 3. You might be wondering, well, how do you know? Well, if you look back at the last one, you saw that this one was 3 square roots of 3. And this one was 2 square roots of 3. And this one was actually 1 square root of 3. And in math, if we find a pattern that works, we use it. Now we can check this, because I can say 8 squared is 64, and 4 squared is 16, and if I take 64 minus 16, I get 48. So this length here would be the square root of 48. But the square root of 48 is actually the square root of 16 times the square root of 3. And I know what the square root of 16 is. It's 4. And so I do get, if I did it the long way, 4 square roots of 3. Now if that pattern always holds true, that means that I have a rule. And I'm going to write the rule here. And again, I'm going to remind us that this is a equilateral triangle, so all three of these distances are the same all the way across. But the distance I want to start with actually in this case would be this distance right here. We're going to call from here to here x. So we'd actually have from here to here is another x. So these distances across the bottom. Now if those distances are x, and again we have a 60-degree angle here, 30-degree angle here, and these are both 90s, 30, 60, 90 triangles. So if this distance is x and this distance is x, that means the distance all the way from top to bottom would be 2x. So this would be 2x. So whatever the halfway distance is, whatever this short leg, we say, the short leg, whatever that is, this one is twice as much. You can see that in each one of these. If this was 3, this was 6. If this was 1, this is 2. If we have 2, we have 4. If we have 4, we have 8. And that's always true with the 30, 60, 90 triangle. The short leg is, take it times 2 and you get the hypotenuse. Or you can think of it the other way, it's half the length of the hypotenuse. The other thing that's always true is the other leg, this leg we used to cut the equilateral triangle in half. If you think about it, it always has the square root of 3 in it, but that number in front of the square root of 3 is the same as this short leg length. So we say it's whatever x is times the square root of 3 gives you this length right here. And so the generalized way of looking at any of these 30, 60, 90 triangles is if you know one side, you know the others. And you don't really need the Pythagorean theorem anymore to actually solve them. So when I look at ones, I have one more on here. So if I said that this length here was 10 from here to here, the short leg was 10. So we call that x, so this is 10. We have our, again, 60 degrees, 30 degrees, and 90 degrees, 30, 60, 90. If these are each 10, then this distance has to be twice as much, or 20. So, and we don't even need to use the Pythagorean theorem to figure that out. We just see, based on the pattern, that it's always true, that the long side, the hypotenuse side of these right triangles, is twice the short leg. And then this length, the other leg of the right triangle, has to be whatever this number is times the square root of 3. And again, we could go back and prove that. We could actually take 20 squared, which is 400, and 10 squared, which is 100. And if you took 400 minus 100, you'd get 300. And we know that this length here would actually be the square root of 300. And the question is that the same as 10 square roots of 3? Well, think about the square root of 300. We could actually say the square root of 300 is equal to the square root of 100 times the square root of 3. And we know what the square root of 100 is. It's 10. And so we actually do get 10 square roots of 3. And so if you think about the original one that we drew, really the unit square, when the bottom length is 1, this column, this center piece, is the square root of 3 tall. And all we're doing as we enlarge it is increasing how many square roots of 3 tall it is each time. 3 square roots of 3 tall, 4 square roots of 3 tall, x square roots of 3 tall, whatever number we have there, 10 square roots of 3 tall. And so with this particular triangle, the 30, 60, 90 triangle, this rule applies and it makes it really simple. All you need is one side of the triangle. You don't really need to use the Pythagorean theorem. You just have to remember the pattern. The base, the short leg, double it for the hypotenuse, multiplex, the square root of 3 times x, whatever that leg is, to find the middle part. And there you have it. That's the way to find the sides of a 30, 60, 90 triangle. All you need is one of the three sides.